All right, let's go through and work the problems. And we'll think a little bit about how we approach the problems. In other words, not just here's the steps of what you're doing, but the why. Why are we doing it? Because we want to know, not just how do we do things, but why do we do things? So that when we're on, say, a test, we know what to do. We know what to do. All right, let's get going. All right, the first problem. Solve the differential equation 3x squared y plus e to the y plus x cubed plus x e to the y minus 2y y prime equals 0. Now, one of the things that jumps out is this is a problem that sort of looks like, it looks kind of crazy, right? We can see some parts of it. Say, look, it's definitely not first order linear because that e to the y, and there's lots of y's showing up in various places. It's not separable. There's no way to really pull this apart to something in x times something in y. And so we say, well, maybe it's exact. In fact, exact is a really good candidate for problems of this type. And what do I mean by this type? Where you have sort of crazy functions attached to the y prime or the dy, and another crazy, yet somehow closely similar function attached to, say, 1 or to the dx, depending upon how we write it. All right, so we're thinking exact. So how do we proceed? Well, let's rewrite it. So what we can say is that this y prime can be thought of as dy dx. So we can think of this as 3x squared y plus e to the y dx plus x cubed plus x e to the y minus 2y dy equals 0. So in other words, we're just writing it in that sort of differential notation, dy and dx. Now, assuming it's exact, we don't know yet, but we're going to proceed like it is, and we'll know pretty soon. We say, hey, the thing that's attached to the dx, this part has to be the derivative of the function we want with respect to x, and the part attached to the dy, that has to be the derivative of the function that we want with respect to y. So we're going to integrate the derivative with respect to x, and we're going to integrate that with respect to x. So we say, okay, so our function looks like the integral 3x squared y plus e to the y times, dx, right? All right. Well, we integrate with that with respect to x. Well, we'll have x cubed y, because remember, y is acting like a constant. So the integral of e to the y, you want to say, oh yeah, integral of e to the y is e to the y, but in this case, it's e to the y times x. And then, of course, we have some constant function, and here it's a function which depends just on y. But we also have that our function, well, we integrate the part that was the derivative with respect to y. So that would be x cubed plus x e to the y minus 2y dy. Integral of x cubed y. Integral of x e to the y. Remember, we're integrating with respect to y. So x is a constant, and the integral of e to the y is e to the y. Integral of minus 2y minus y squared plus some function that only depends on x. Now we can tell whether or not we're exact, and if it is, we're just a hop, skip, and a jump away. So what we do is we say, all right, look at the pieces which only involve, which involve both the variables. So in other words, they have both x and y. And do they match? Well, yeah. So they both have pieces, x cubed y, and they both have pieces, x times e to the y. As long as those pieces match, we're exact. And then we have to do is say, okay, are there any exceptional pieces? In other words, something that depends only on x, something that depends only on y. And there is this little piece right here. And now we put them all together. And so we say, aha, the function that we're after has the form. So here's our function, f of xy. Well, it's x cubed y plus, well, e to the y times x, or x e to the y, doesn't matter what order you write things in, x e to the y, and minus y squared. Now, that's not our differential equation. Our differential equation is equals some constant. And remember there's an initial condition here. So how do we do the initial condition? Well, now what we'll do is we'll come in here, and we're going to plug in x equals 2 and y equals 0. And what happens? Well, 2 cubed is 8, and times 0 is 0. 2 times e to the 0 is 2. 0 squared is 0. So when we plug x equals 2, y equals 0 into this part, out comes 2. Well, that says then, lo and behold, that c equals 2. So our final answer, we can now say, is x cubed y plus x e to the y minus y squared equals 2. And we're done. That's it. That's not so bad. In fact, sometimes when the problem looks kind of hopeless, it actually is like, oh, there's a nice method, and it's pretty clean, pretty slick. So, it's, don't get discouraged if things look bad. It could actually be good. Wow, isn't that great? All right, well, that's just one problem. We got more to do. On to our second problem. So find the general form for solutions of the differential equation, where we have the fourth derivative of y plus 8 times the second derivative of y minus 9 times y equals 0. All right, so this is our constant coefficient, linear, homogeneous. We're like, nice. We have ways to do this. And what we do is we say, all right, we start with our differential equation, and we transform it into our characteristic polynomial. So that's r to the fourth plus 8 r squared minus 9 equals 0. And now we have to find our roots. And at this point, you're probably thinking, ooh, fourth degree. That looks like it could take a while. But actually, let's kind of stare at this for a second. We shouldn't give up hope just yet. And is it fourth degree? Yeah, it is. But could we think of it in another way? And you might be like, oh, where are you going with that, Steve? Okay, so here's sort of where we're going. Think of this as, instead of r to the fourth, as r squared squared, and then plus 8r squared and minus 9. So in other words, it's essentially a quadratic. It's just a quadratic where instead of r, it's r squared. So okay, that's not so bad. And we're usually pretty good at factoring quadratics. So for instance, in this case, can we think of two numbers that multiply together and give us -9, but when added together give us +8? It's not too hard to think of numbers that do that, namely 9 and -1. So that's saying, hey, let's try this factorization. R squared plus 9, R squared minus 1. Now, we should always check, right? So we get R squared times R squared, to R to the fourth, minus R squared plus 9R squared, it's 8R squared, minus 9. We say, hey, that's looking nice. So this R squared plus 9 equals 0. R squared equals -9, which gets us to the roots, taking the square roots here, plus minus 3i. R squared minus 1, well, that's 0 if R squared equals 1, which gets us to our roots plus minus 1. So they're all distinct roots, so we don't have to do any bumping here. And we have 4 of them, which is what we expect because it's fourth degree. And so we say, okay, great. So now we're ready to write down our general form. So for plus 1, that'll be some constant because we want general form. We're not just listing the functions. We want constant times this plus constant times that. Okay. So plus 1, so it would be e to the 1 times x, which we'll write that as x, minus 1, that's our next root. So that'll be e to the minus 1 times x, which we just write as minus x. Now we come here. These are complex roots. They're actually pure imaginary. So these will translate into sine and cosine with the 3 on the inside. So plus c3 cosine 3x plus c4 sine 3x. And we're done. Now you might want to say, does it matter which order we write them in? No, doesn't matter. We just need to have all 4 of them in some order. You might also say, well, do we have to use C1, C2, C3, C4? No. You could have done A, B, C, D, or just any 4 symbols to stand for constants, as long as it's clear that that's what you're doing. All right? That one's not so bad. Wow. We should have some of those on the exam, right? It'd be great. Well, maybe. Number 3. So a spring mass system with no external forces has been created with m equals 4, c equals 40, and k equals 84. All right, so let's remember what spring mass systems are. And so in particular, they take the form of m x double prime plus c x prime plus kx equals 0. And here they say, look, we have the values for these parameters. So we'll say, all right, that means 4x double prime plus 40x prime plus 84x equals 0. Great. Now, we're given that initially x0 equals 2 and v0 equals 6. Now, x0, we think of that as our position at 0. v0 is our velocity at 0. So we should really think of this as the derivative at 0. And now we want to find the solution for the system. After we do that, there's another part that says also classify the type of damping that is exhibited. Is it critical damped, underdamped, overdamped, undamped? All right, well, let's do the first part. We can't classify until we figure out the behavior. So where to go? Well, let's start. Let's clean it up a little bit. Notice we can divide everything by 4. So we can say, all right, this is x double prime plus 10x prime plus 21x equals 0. Turn that into our nice polynomial, r squared plus 10r plus 21 equals 0. Well, it's quadratic. We like quadratics. Can we think of two numbers that multiply together to give 21 and add to give 10? Yeah, it's not too hard. 3 and 7. So that says this factors r plus 3, r plus 7. And so we have our roots are -3 and -7. Okay, so that tells us that the general form for our mass spring system for position has it in the form some constant, let's say a e to the -3t, plus some other constant b e to the -7t. Okay, so we're told that 2, well, that's our x at 0, and, well, that'll be a plus b, because it's really easy to work with when we have e to the 0. Beautiful, beautiful thing. How about x prime of t? Well, easy derivatives here. That'll be -3a e to the -3t and -7b e to the -7t. And, okay, and then we have 6. That's our, again, our x prime of 0. Well, that's -3a and -7b. So we have two equations, two unknowns. Ah, nice. That's, I like to call it our bread and butter. Just because we see it so often, we should be super comfortable with carrying it out and doing the computations. Right? Yeah, of course we should. All right, so let's write those equations again. A plus b equals 2, and -3a minus 7b equals 6. So we start thinking about what are ways we can combine these together and get something nice, in particular get, say, cancellation. Well, we can take the first equation and multiply it by 3, and what happens? Well, if we do that, we'll have 3a minus 3a, that's 0. Then here we'll have 3b minus 7b, well, that'll be minus 4b. And then we'll have 6 plus 6 equals 12. So that tells us that b is -3. All right, so b is -3. Come back in. So we say a minus 3 equals 2. So we're replacing b equals -3. And therefore, a is 5. All right, great, good. And, okay, now what? Well, that tells us, see, what do we want? We want to find the solution for the system. We basically have it, because there's our general form. We solve for a and b. So our solution for the system is x of t is equal to 5 e to the -3t minus 3 e to the minus 7t. And that's it. We're done. Now, the classify. So we have to think about what's going on. So some things we might just have it memorized, and other things we might have to sort of think about. So undamped is if there's no damping, which means C would be 0. Okay, so it's not undamped. So we can cross that one out. Underdamped says there's just a small amount of damping, so it should still behave like a spring. In other words, we should still see oscillations. So if we expect it to be underdamped, we just want to see sines and cosines, which we don't. Okay, so it's not underdamped. So that leaves us really two possibilities, critical damped or overdamped. Now, critical damped is right on the edge. And so what happens in critical damped is the roots have to repeat. And here the roots don't repeat. So it's not critical damped. And so that leaves us process of elimination, overdamped, or we could have just jumped right there. Said, look, we can see there's no oscillation going on because there's no sine cosine, which means we're either critically damped or overdamped. And when we see distinct roots, that means we really have a lot of damping on, so it's overdamped. So this is an overdamped problem. And that's the other part. And that's it. Yay! Haha! That one wasn't so bad. Well, hopefully none of these are bad. And that's the goal. So we want to be able to do them all. All right, number 4. Solve the differential equation xy prime equals y log x minus log y plus 1 with y of 1 equals e cubed. Now, let's be honest here. Oftentimes when they give us the differential equation, they may not give it to us in the easy to recognize form. And so we have to be willing to be flexible and say, okay, can we move things around? Now, there's a couple things we can roll out pretty quickly. It's not linear first order because that log y, okay, hopeless. It's not separable. There's no way to pull that log x and log y apart into multiplication. Kind of hopeless. Great. So it's not linear first order. It's not separable. Is it exact? Well, it doesn't feel like a candidate for exact, because usually when something's a candidate for exact, you'll see like a function plus something y prime or something dx plus something dy. Given that they write it this way, it's probably trying to say, don't think exact. Which means, what are we down to? Well, now we start thinking about maybe there's a good substitution to make. And we also notice they gave us logs, and we know things about logs. So let's remember things about logs. In particular, notice here we have a subtraction. So when we have subtraction, we can say, look, subtraction really becomes division. And then we're saying, ooh, x over y. That feels like homogeneous. So that's where we're going to be going. So we're going to say, let's try homogeneous. Because when we see that, look, there looks like ways we can rewrite things so we can get that, y over x, well, x over y is essentially y over x just flipped over. Then, let's try it. Let's see how far we can get. So what do? Well, I can take the x, divide it, so we could say y prime is y over x. Now here, log x over y, I really want to think of it as log y over x. So if I flip the inside, how does that affect the log? Well, turning things over is the same as taking something to the negative 1 power. And so properties of logs says that puts a negative in front. So minus log y over x and plus 1. All right, now the substitution to make. We're going to make, say, z. Of course, you can use any symbol you want. Say, it might be v, w, whatever symbol you like. It's y over x. Or if you like, you can say, look, y is z times x. And so we can say y prime. Now we do the product rule. Say the root of the first times the second plus the first times the root of the second. And we get that. Because here when we're talking about derivatives, we're taking the derivative with respect to x. All right. So we have our pieces in place for our substitution. We have our expression is in the right form. And now we do our substitution. Let's see what happens. So we have y prime will become z prime x plus z. And that's going to equal here y over x, z. And we're going to get minus log of z and plus 1, which you'll notice you can distribute here. So this becomes minus z log z plus z. And then we're like, ooh, hey, check it out. We can get some cancellation. Nice. Good stuff. So, well, okay. So we can say here, we really have x dz dx is equal to minus z log z. And remember, when we do a homogeneous substitution, it's going to lead to something which is separable. So this is separable. So we say, okay, what does this become? Well, 1 over z log z dz is equal to minus 1 over x dx. And that's our separation. And now the next step. So after we separate, we integrate. One of these is not too bad. So on the right-hand side, that's minus log of x, and plus a constant c. Now, what about the left-hand side? Well, things get a little bit more interesting here on the left-hand side. Now, you might say, that looks kind of hopeless. Unless you say, maybe there's some hope, because think of substitution. Suppose you let u be log of z. Then what's du? Well, be 1 over z dz. In other words, that part right there is du. So what you would have, this would become the integral 1 over u du, which is log of u. We don't need the plus c because it'll be over here. But u is itself a log. So we get log log z. All right, so updating. We are now into sort of our simplification stage. So log z is equal to minus log x plus c. Okay, well, now what? Well, next thing we can do is, let's raise both sides to the power e. So, that'll say log of z is some constant, right? Because we're taking e, so we got just one log. So e to the constant is a constant. E to the minus log x is 1 over x. Good. And, all right, that's not so bad. We can even go one step further. And, okay, what is z? Well, that'd be e to a constant over x up in the exponent. But what is z again? Well, this is really, our substitution is y over x. So we can say that z, y is equal to some constant x, e to the constant over x. Okay, so that's the general form. But we have an initial condition, so let's solve the initial condition. All right, we have space up here. Might as well use it. So what's our initial condition? When we plug in x equals 1, y equals e cubed. So let's see what that gets us. So we have e cubed is equal to 1 times e to the c divided by 1. Well, all right, from here we can see that it really says e cubed is e to the c, so that tells us that c has to be 3. And so our final answer is y is equal to x e to the 3 over x. That's it. We're done. Nice. Wow. And that's our halfway mark. great. Good. Let's keep it going. Next problem. Solve y prime plus tangent of xy equals cosine squared of x, where y of 0 is minus 1. Okay, now here, when we look at it, we should notice that there's not very many places where y shows up. In fact, there's just two, y prime and y. So when we see a single y prime and a single y, and we should think, is this linear first order? And the answer is yes, it is. And we're like, great, wonderful. So let's use that technique. Now the next thing we do is we say, okay, what's in front of the y prime? Now in our case, what is in front of the y prime? You might say, well, there's nothing, and that really means there's 1. That's the right thing we want. So we don't have to do any rewriting. So we're like, wow, this is set up for us to just go for it. So what do? Well, we say this part, what's the y? That's our p of x. So we want to do e to the integral of p of x. Well, all right, that's e to the integral of tangent. Now, do we know the integral of tangent? Yes, it's on our list of things we should know. The integral of tangent is natural log of secant, meaning we get secant. That's our multiplying factor, our integrating factor. So, in particular, we get that secant of x, y prime, plus secant x tangent x, y, equals secant of x times cosine squared of x. Now, secant times cosine squared, well, cosine and secant are related to each other in a nice way. Secant is 1 over cosine. So this actually simplifies to a single cosine. By design, this is why integrating factors work, this left-hand side is the derivative of the integrating factor, secant of x and y. So we say, all right, great. Now what we'll do is we'll integrate both sides, and then we'll be almost done. All right, so we're going to integrate with respect to x, integrate with respect to x. Very easy integrated derivative. So we'll have secant of x times y. Integral of cosine is sine, or is it negative sine? No, it's positive sine. All right. Yes, we saw the sign, and it opened up our eyes. We saw the sign. Don't forget the plus c. Now, we can finish off solving for y. Well, we can divide by secant, which is the same as multiplying by the reciprocal. Well, secant is 1 over cosine, so multiplying by the reciprocal says multiply through by cosine. So y equals sine of x, cosine of x, plus some constant c, cosine of x. So that's the general form for a solution, but we also have that initial condition left for us to satisfy. So let's satisfy that initial condition. We're told y of 0 is negative 1, so we have negative 1 equals sine of 0, cosine of 0, plus c times cosine of 0. Well, sine of 0 knocks that term out, and cosine of 0 is 1, so we get negative 1 equals c. And therefore, our final answer is sine of x, cosine of x, minus cosine of x. And that's it. We're done. Wow. Yay. All right. Well, these aren't so bad. We're doing wonderful. So let's keep going to number 6. So here we have y prime is negative the absolute value of y squared minus 1 times arctangent of y. This is a really ridiculously hopeless differential equation. No way we're going to solve it. And that's okay. We're not going to. We can actually see what kind of problem this is. Even without reading the rest of the statement, we say, hey, wait a second. This is our y prime equals f of y. In other words, we are in an autonomous differential equation. So it's like, nice. So we know how those work. We don't have to solve any differential equation here. We're really after, hey, what's the aspects? What's the behavior going to be? Okay, so first step, find all the critical points. Critical points, you can think of those as constant solutions. And how does that work? Well, that says when is this right-hand side equal to 0? So for part A, we're going to have negative absolute value of y squared minus 1, arctangent of y, is equal to 0. Well, okay, we have two pieces, arctangent of y, and this absolute value of y squared minus 1. Now, when does arctangent equal 0? We know a little bit about arctangent. It's a great function. It turns out it equals 0 in one place. Arctangent of 0 is 0. And that's because the tangent of 0 is 0. So that gives us a solution y equals 0. Here, y squared minus 1, because if we want the absolute value to be 0, what's inside has to be 0, which means y squared better be 1, which says y equals plus or minus 1. And therefore, we've found there are three critical points. 0, 1, negative 1. Okay, there we go. There's part A. That wasn't so bad. Now, part B. Draw the phase diagram. Okay, so how do we do that? Well, we draw a line. We mark our values. So we have 0, 1, minus 1. So we put them in order. And that chops up our line into 4 pieces. And now we have to think about what's happening to the sign on each piece. Now, in some sense, we are in a bit of luck. Notice, what can we say? Well, the absolute value, this part, what's true about the absolute value of something? It's always positive. It's a very optimistic function. It's always looking on the positive side. So we say, okay, so the only thing that can affect the sign is this arctangent of y and this negative. Now, what do we know about arctangent? Okay, well, let's see. We can do a quick sketch of arctangent. See, arctangent normally looks like this. It's like you took a piece of tangent and sort of turned it 45 degrees. All right. So it's positive when we're above 0. It's negative when we're below 0. The negative just flips it around. So what's the result? Well, what we've done here is we've just gone through and reasoned. If we're above 0, then we have the y squared minus 1 absolute value is positive. The arctangent is positive. The negative makes it negative. So we have y prime positive, y prime positive. On the other hand, if we're below 0, okay, absolute value is positive, the negative is negative, and arctangent is negative. Negative, positive, negative makes things, whoops, I put positive here. It's negative. Ha ha ha. Catch yourself, right? Right? So negative, positive, positive makes things negative. Negative, positive, negative makes things positive. Okay. Now, we're not done with the phase diagram. We need one more thing, the arrows, which is saying how do things change. So when we're positive, we put arrows to the right. Means we're going up. When we're negative, put arrows to the left. Means we're going down. Okay, so there we go. There's our nice phase diagram. And we're halfway done with the problem. Okay, oh, that's not so bad. It gets kind of long, right? A, B, C, D. It's like, oh, but each part, it's like, oh, all right, not so bad. Okay, so the third part of the problem, part C, classify. So we have negative 1, 0, 1. Now, we look at the arrows. Negative 1, we go right, right. So we're just do. Okay, so what's happening? Well, we're coming in on one side, but we're going out on the other. That means that negative 1 is semi-stable. 0, we can see it. We're going in, right? So that's pulling things in, and that is stable. Now here, we have arrows going to the left, right? And so we're coming in, but we're also going out. So that's, again, semi-stable. And that's classification. once you have the phase diagram, and you remember what goes with what, it's pretty quick. Okay, now part D, and this is a long statement, so we got to sort of absorb this. For each critical point, so there's boom, 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 determine all the y0 for which the solution to the ODE with initial conditions y of 0 equals y0 will have y approach the critical point as x goes to infinity. So you might think like, whoa, okay, hold on, what is this saying? Because that's a little bit hard to parse that statement. It's saying, well, if I throw in an initial condition, where does it go? And basically think about all possibilities. So how do you figure that out? Well, the answer is, suppose I say initially I'm at 2. So I'm here. What do? I follow the arrows to the critical point. So it says if I'm at 2, follow the arrow, you go to 1. If I'm at 1, well, you stay at 1. What if I'm at -0.5? Follow the arrows, goes up to 0. If I'm at -1,000,000, way over here, follow the arrows. It'll go up to -1. So the arrows tell you where you go. So now we say, okay, where do we start? And we can end up at various places. So here we go. Suppose I want to end up at -1. Well, if I start below -1, that's great because I'll move up. If I start at -1, that's fine. But if I start above -1, nope, I'm going to be moving away. So for -1, if I want to end up at -1, I can be anything less than or equal to -1. So that says we have the y0 is anything less than or equal to -1. How about for 0? Well, so if I want to end up here, I can move from below or I can move from above. Now, how far down can I go? Well, I can get anywhere as long as I'm above -1. As soon as I go below -1, I'm going to end up at -1. So, okay, so from -1, not including -1, or I can go all the way up to 1, but again, not including it. And so we have -1 less than or equal to y0. Even after I just said it, strict inequality, less than 1. So as long as our initial condition is anywhere between -1 and 1, we will move towards 0. For 1, well, if I start anywhere above 1, I'll move down. If I start over here, I'll move away. So as long as I start above 1 or even at 1, I'm okay. So now it's anything bigger than or equal to 1. And that's it. That's the answer. All right. I probably made that look too easy because I'll be honest with you. I knew this problem before I worked on it because I wrote it. But if you're confused about something on an exam, there's this wonderful thing called raise the hand. And how does raise the hand work? Well, you take your hand and you raise it. Yeah, that's it. That's how raise the hand works. And you can say, can you try to explain this a little bit? And they might say, well, maybe a little bit. But, they can't give you too much, but they'll try to help you. It's worth a try, right? It's better than just sort of sitting there being flustered. All right, there's still 2 to go. All right, good. Number 7. On the planet Zizix, in case you're wondering, is Zizix a real word? It's actually a town in California. There's a place called California. And if you ever drive between Los Angeles to Las Vegas, which a lot of people do for some reason, there's an exit off the freeway very close to the the Nevada border. That's called Zizix Road. And so, all right. So anyways, on the planet Zizix, a ball dropped from a height of 20 feet hits the ground in 2 seconds. If a ball is dropped from the height of 200 feet, how fast will it be going when it hits the ground? It's very interesting that they chose to, on this planet, to use the imperial units, but all right, no problem. So what do we have? So let's just draw a picture. So here we have a 20-foot, and we'll we'll come here and we drop. And it takes 2 seconds. Now, let's think about it. What's going on here? Is this really differential equations? Well, this is sort of early differential equations in that it really says, hey, this is about motion. And so we can say the second derivative, well, what affects it? If you drop a ball, the only thing affecting it is the gravity. Now, we don't know what the gravity is on physics, so we'll call it G for gravity. And then we say, okay, the first derivative, well, we integrate. It's gravity times time plus some constant c. Now, we dropped it, which means that there's no initial velocity. So we can say x prime is 0 equals 0. That equals 0 plus c. So we say, aha, updating x prime is really this gravity times c. And I should really point out this should be negative here, just because we think gravity points down. All right. Now, the function. So that's minus 1/2 gravity t squared plus some constant d. Now, what is that? Well, we're dropping it. Now the question is, where do we drop it from? We drop it from a height of 20 feet. And so we say, okay, we'll say that x of 0 is 20. So that says, look, that's equal to d. So our position is x equals minus 1/2 gravity times squared plus 20. Okay, we're making great progress here. Now, what do we use? Well, we have our position function, and we're told it hits the ground in 2 seconds. Okay, so how do we use that? Well, we can say, look, we know x of 2, it's at ground level, which means 0. So that's minus 1/2 times gravity times 2 squared, which is 4, plus 20. Well, all right. So 1/2 times 4 is 2. So we really have minus 2g plus 20 equals 0. And so gravity is 10. Now we're not done, but now we know on physics they have a very curious gravity that works out really well. Must make their physics classes super easy to have such nice numbers. Okay, so that's our gravity. Now where to? Well, the next thing to do is to say, look, we're going to now drop it from a very tall place. So again, here we are, and we're going to drop our ball, and it's going to fall down. But now this is at 200 feet. And the question, of course, is how hard do we hit when it lands? So, well, not how hard, how fast. That's saying something about the derivative. All right, so now we'll go through it again. So now we say, okay, our second derivative, well, it's minus 10, because we know what gravity is. Our first derivative, minus 10 times t plus some constant c. But again, we're dropping it, and so we can say, look, x prime is 0, that's c. So updating, we have our velocity is minus 10t. And so if we knew what time we hit the ground, we'd plug in t, and we'd be done. Well, we keep going. So another antiderivative, we'll have x is minus 5t squared plus some constant d. Well, how do we find that? Well, we say, look, when we released, we went a height of 200. So that says, plugging in 0, that we get d equals 200. All right, so our position function, minus 5t squared plus 200. Now, if you want to know when we hit the ground, set it equal to 0, solve for t. So we'll end up with 5t squared equals 200. T squared, well, 200 divided by 5, 40, and then take the square root. no plus or minus. Time moves forward. And so the square root of 40 is 2 times square root of 10. So put that in to our velocity, and we come to our conclusion that x prime, at the moment we hit the ground, well, it's minus 10 times 2 times square root of 10, or minus 20 square root 10. And if we wanted to, we'd throw in units, but that would be if we're in a physics class. It didn't tell us to do units. Do we know what the units are? We do, because we can see it. It's feet in seconds. So feet per second. And you might say, do I need the negative or do I not? Well, it depends. Do you interpret fast as speed or velocity? But I think that whoever is grading should be capable of saying, I'll take either. All right, so there we go. That one wasn't so bad, which brings us to our final one. Okay, number 8. Solve y prime equals minus y log y sine of x. And now, like, wow, this is number 8? It seems pretty straightforward. Yeah, what is it? Well, you have some y stuff, and then you have some x stuff. In other words, this is separable. And we're like, we love separable. And we should have started with this one. Keep in mind that we may not necessarily go in the chronological order, or the problems may not necessarily go easiest to hardest. It's just the problems are the problems. So don't try to overthink the problems. Don't be like, oh, well, this is the second problem on the exam, so it must be kind of early in the material we talked about. Not necessarily. You don't know. So just do the problems. That's good advice. Do the problems. All right, so what do we have? Well, okay, so if we separate, we can move the y log y over. So dy over y log y is equal to minus sine of x dx. Integrate. Well, the integral of minus sine is cosine. Tack on a constant c. So you can check. What's the root of cosine? Negative sine. Now, integral of y log y downstairs. We actually just did this a few problems ago, so I'm not going to repeat it, or at least I won't rewrite it again. Okay, maybe we should. Keep in mind that when people are grading, that the person who grades problem 2 is going to be different from the person who grades problem 6. And so you can't say, oh, they'll see I did the work on problem 2, and they'll just know I did it. Not necessarily. So we should, in the sake of completeness, we'll say, okay, look, integral dy over y log y, we'll let u equal log y, du equals 1 over y dy. This becomes 1 over u du, log of u, which is log y. And the reason I'm not putting a plus c is we already have a plus c there. So here we go. Log y is equal to cosine x plus c. And since they didn't say solve for y explicitly, that's good enough for us. This is an implicit, it's a true statement, and it's a solution. We don't have to solve for the constant. And that's it. That was the last one. All right, good. Well, I hope you did well, and I hope you did well in the real exam too. All right, see you later.